Okay, and I think the pace of everyone entering the room has leveled off. So, Rebecca, take it away.
Okay, thank you. Okay, so welcome to all of you who have joined us today for this webinar on the best practices for PhysChem determination using Pion Sirius T3. My name is Rebecca Ruiz, and I'm the Global Analytical Service Manager at Pion. This talk is oriented towards Pion Sirius T3 users who are performing daily analysis using the T3, or users who are using the software to process the data. The webinar, so we have a duration approximately of 40 minutes. And if you have any questions during the webinar, please write your questions using the Q&A chat box, and the question will be collected and answered at the end of the webinar. The webinar is organized in a way that the basics are shown at the beginning, and while the presentation is progressing, more advanced material will be shared. This presentation will start looking at the daily instrument tasks, which are showing in the maintenance tab. It will be a review of the instrument calibration, covering electrode calibration, blank, and base standardization. It will follow a close review of the PhysChem measurements, pKa, log P, and solubility, including experiment design and quality of the data obtained for every T3 technique. The webinar will finish with a quick look at the Pion Sirius T3 user maintenance guide. So let's start with the daily instrument maintenance. So before starting any experiment, all the warnings shown in the maintenance tab needs to be resolved. The software shows which modules need attention from the user and what needs to be done. For example, in this screen, we can see that from the dispenser module, we have the warning automatic flash due. Additional, one or more dispensers need to be refreshed or installed. From the titrator module, we have a warning to refresh all the static liquids. The electrode needs to be refilled as well, and the spectrometer calibrated. And for the autoloader module, the ultrasonic bath needs to be refilled or topped up. Maybe some of you have a different T3 configurations, and you will have a different screen than this one, for example, without an spectrometer or without an autoloader, which means without the ultrasonic bath, for example. So every day, the instrument will flash automatically all the dispensers. In this case, the flash wasn't done. The reason could be that maybe the instrument was closed down, or because the instrument was in use. In any of these cases, once the instrument is inactive for a period of time, the flash will be done automatically, or it can be done manually. By clicking on the highlighted yellow dispensers, in this case, here is the water, is shown in the reminders here below why this item is highlighted. So the ISA water is lower than the minimum volume required, that is 50 milliliters, and the bottle needs to be refilled. The way the reminders are defined for the dispensers is shown in this slide. Mainly, they are defined by minimum volume, expire dates, and automatic flash. Please check that your control software has these reminders and change them accordingly if not. So the expire date for the base is 3 months. However, I recommend to change this reminder to every month, as the base needs to be standardized regularly to determine the carbonate levels. So every day, all the liquids in the sample the sample state needs to be refreshed. And by refresh means dispose the liquid to the waste, clean the vial, and add the new fresh liquid into the vial. It's important not to use the same vial again without cleaning it, especially with the buffer vials and the storage solution, because with time will start to appear bacterial growth on the bottom of the vial. So as is shown in this slide, by, for example, clicking on the items, in this case is the flowing wash, we will show why this one was highlighted. This slide shows how the reminders are set up for the sample stage. It's by volumes and expire dates. The volumes are defined in a different way from the dispensers, as the sample stage contains the flowing wash and the waste reservoirs, which are connected to two containers usually placed on the floor below the instrument. So for instance, in the volume, if the volume of the flowing wash container is lower than 500, it needs to be refilled. Or if the volume of the waste container or drain is higher than 9 liters, then needs to be emptied. The spectrometer needs to be calibrated every day. And the way to do it is making sure that the intensity counts of the maximum peak, which is between 200 and 400, needs to be between 56 and 62,000 intensity counts. So meaning that it needs to touch this green area on the top of the graph, not higher and not lower, as we need a green signal between the 200 and 400 nanometers. Just a reminder that the maximum integration time is 100 milliseconds. So it's recommended to keep a daily record of the milliseconds in order to observe any abrupt changes in the intensity. If this is the case, it could mean that the UV probe is dirty or the mirror is damaged, or as I have shown in this slide, the hours of the lamp have exceeded the recommended 1200 hours, and so the lamp needs to be replaced. The lamp time is not part of a reminder, so time to time, please keep an eye on the lamp hours. The electrode needs to be refilled with filling solution every 7 days. It's recommended to do it every Friday, because once the electrode is refilled, it needs a time to stabilize. So refilling the electrode on Friday leaves the electrode enough time to stabilize during the weekend. Remember that the optimal millivolt range readings at PhysChem are plus minus 30 millivolts. So it's recommended to keep records of the millivolts readings, as the electrode deteriorates with time and the millivolts change. If the millivolts are higher or lower than 30 and minus 30, the electrode needs to be replaced. The ultrasonic bath needs to be refilled or refreshed, depending on the state of the water, every week. Instrument calibration. Instrument calibration includes electrode calibration, blank, and the KOH standardization. So looking at the daily calibration, at the beginning of every day, 2 cleanups in each direction needs to be performed. First one, high to low, and the second one, low to high. These 2 cleanups are cleaning the probes from the previous assays performed the previous day. So then the blank is performed, and with the blank, the electrode is calibrated, with the blank, and the blank needs to pass. Monthly calibration includes the daily calibration plus the standardization of the base. With the base standardization, the carbonate content is checked. So by base standardization means 3 KHP titrations are carried out. Multiset is created to obtain the average of the 3 titrations, and needs to set the new base concentration factor as the new import default value until the next standardization happens. And finalizing, a blank needs to be titrated again. So to talk about the blank, it will need another webinar, but for the purpose of this presentation, the next slide will explain briefly why the blank is important and share a couple of tips to help to recognize what is failing in the instrument when the blank is failing. So why it's important that the blank passes? Firstly, the blank defines the 4+ parameters, alpha, S, GH, and GOH, to obtain the working pH. This is the pH scale in concentration, because the software performs the calculations in concentrations to determine the PhysChem properties, pKa, log P, and solubility. Secondly, a bad blank may indicate problems. For example, a blockage in the capillaries, a leak in the syringes, stirring problems, inert gas flow low, problems with the electrode, and also contamination in the system. Blanks are also important as they standardize the acid and determine the carbonate levels in the system. Where to start to investigate when the blank is not passing? As you know, the base and the acid have similar concentrations and both have 0.5 molar as at the concentration, which means that the amount of base required to titrate from 1.8 to 7 pH should be similar to the volume of the acid already used to adjust the pH from 6.4, 6.5, this will be the pH of the ISA water, the pH at the beginning of the say, to 1.8. So, and moreover, the final volume at the end of the curve should be the double of the base used if we compare with the volume of the acid used at the beginning. So, these volumes are shown in the tab Events. So this slide shows a good blank. So if we look just what I said, so here around pH 7, we have that the volume of the acid is more or less the volume of the base. And at the end of the titration, we have that the volume of the base is more or less the double of the volume of the acid. Not only that, at the beginning of the say, we have the initial pH. This is the pH, as I said, the ISA water, that usually is around 6.4, 6.5. So for example, if you have a blank that failed and you are looking at this screen to the volumes at around pH 7, you observe that, for example, the volume of the acid is lower than the volume of the base. This could mean that it's a leakage in the acid dispenser, or maybe the base could be blocked. So to check the acceptable range values of the blank parameters, you can use control and refinement software. As this setting can be found by clicking the diamond symbol, which is the refinement settings. It's highly recommended to keep records of the 4+ parameters from the blanks, the volume of the acid used to adjust the initial pH to 1.8, the acid concentration factor, the carbonate, and the millivolt readings from the electrode. Because if abrupt large deviations happen, this will indicate problems in the system. So, but however, remember that if there is a problem in the system, the blank will fail. These records are to track any tendency in the system which will end up with a bad blank. The advantage of keeping the records is that when the blank fails, it will be much easier to identify the problem. Now that the warnings in the maintenance tab are resolved, the blank pass, and the K8 standardization is done, then the instrument is ready to perform the determination of any physical chemical properties. So let's start with ionization constant. For pKa, Sirius T3 offers two techniques, the spectrometric and the potentiometric. For the spectrometric determination, we have the fast UV and the UV metric analysis, which I will talk about in the next slides. However, for both assays, fast UV and UV metric, 5 microliters of 10 millimolar DMSO sample stock solution plus 25 microliters of buffer is needed. This technique, the spectrometric technique, measures pKa's between 1.5 and 12.5, and sometimes even lower and higher than this range. And only UV active and ionizable centers could be determined. But for potentiometric technique, more sample is needed, and between 0.5 and 1 milligrams, depending on the molecular weight of the compound. The range of the pKa's which can be determined is narrower, between 3.5 and 10.5. However, it can be determined pKa's for UV or not UV active compounds. Both techniques could be carried out in aqueous media and with the use of co-solvents if the sample is poorly soluble in water. So, as I have mentioned in my previous slide, so T3 offers two analyses for the spectrometric technique, the fast UV and the UV metric. The main difference between them is the buffer. And because the buffer, these two analyses have different limitations and advantages. So the buffer used in fast UV is the neutral linear buffer, a buffer made by Pion, which contains several acids and bases, which allows the solution to be buffered between pH 2 and 12. So the idea is collect the data without waiting the pH readings to be stabilized from the electrode. So the titration is fast. The consequence of that is 6 minutes per titration. The pH working range, as I say, is 2 to 12. 250 nanometers is the minimum working wavelength to use because the buffer absorbs below this wavelength. UV metric uses phosphate buffer. pKa's can be measured between 1.5 and 12.5 or even lower and higher of this pH range. The titration is 20 minutes per titration. The duration is longer as the pH readings needs to stabilize, and the minimum wavelength is around 235 nanometers. If in this picture is show the use of the reference called as fast UV buffer calibration for the fast UV assay and reference for the UV metric assay, which I will talk about this reference in my next slide. So, however, I would like to show here that fast UV analysis, because it's a screening analysis, only use one buffer calibration and only is using one that is going to be used for the rest of the samples that is going to be titrated in the same conditions. However, for UV metric assays, every reference has their own sample. So always we have in couples. So both reference, the fast UV and the reference for UV metric, contains the same media as the sample, but without the sample. So meaning that if, for example, I'm using 5 microliters of 10 DMSO stock solution in my vial with the sample, that means that I have to add 5 microliters of DMSO in my reference. If I dissolve my sample in methanol, then I have to add my 5 microliters in methanol. If I add 10 microliters, 10 microliters. If the media of the experiment changes, for example, I'm using dioxane, then reference will be run in dioxane. If the temperatures change to 37 degrees, reference will be run at 37 degrees, and so on. How good is my data? As both analyses, fast UV and UV metric are spectrometric analysis, data processing is the same, and the same software display will be applied for both. To have a good data, the species which are involved in the pKa's needs to be different. And by different, I mean different spectra. And this point is really crucial because the pKa's are determined based in the changes of the absorbance with the pH. So during data processing, the experimental points, the triangles, needs to fit the theoretical lines. The optimal absorbance range is between 0.2 and 1.5 units. Lower than this range, the UV data is poor and weak. However, higher than 1.5, the detector is saturated and will show this typical flat shape. Now I'm going to present the potentiometric technique. For this technique, it's advisable to weigh the sample in the vial as a solid. The amount of sample depends on the formula weight and the molecular weight. And for that, the buffer index profile needs to be checked to assure that the experiment will be run with enough sample. It needs to take into account that during the experiment, not only the sample is titrated, the media is titrated as well. So this is why the amount of sample has to be higher than the buffer capacity of the media to be able to obtain good results. In this slide, I have an example of a sample with two pKa's. The second pKa, the blue file, this is the first pKa, second pKa. So the second pKa, you can see that is well defined because this second pKa is the sample is over the buffer capacity of the media. However, the first pKa here is under the curve. And you can see that we have little data, so not enough to calculate, to determine a pKa. However, if we increase the amount of sample, then the first pKa can be determined, and you can see it. This is the red file, so you can see that we have more data, so enough to determine the first pKa. In relation to the previous slide, we recommend that the initial sample concentration will be around 1 millimolar. You can find this information when you check the buffer capacity index profile during the setup of the experiment. Also, for a good pKa result, the model design needs to include the formula weight and molecular weight with all counterions, the aprotics, the ones that they don't have pKa's, and the protics, the ones that they have pKa's. Always start when the sample is ionized. So that means low pH for bases and high pH for acids. And this will have the dissolution of your sample. If the sample precipitate in aqueous media, then use co-solvent. And perform at least 3 titrations at different percentages. In the case of methanol, don't use percentage higher than 65, as Yasuda-Shedlowski extrapolation is not longer linear. And if you would like to know the type of ionization of your pKa, that means if the pKa is a base or an acid, use the linear extrapolation instead, Yasuda. So, for example, here in this graph, the rule is if we are increasing the percentage of co-solvent and the pKa increases, we have an acid. If we increase the percentage but the pKa decreases, we have a base. However, please take into account that this rule is not 100% effective because we have always different interactions that occur in solution between the solvents and the solid. How good is my data in potentiometric technique? Check the buffer index of the sample, especially the third titration, because it's where the sample is more dilute. No errors and warnings has to appear in the file after processing the data. The experimental points, the triangles, need to fit the theoretical line. Check that there is no precipitation. The software will highlight with a yellow area any precipitation detected. If this happens, then repeat the sample using co-solvents, or if you have already used a co-solvent, then increase the percentage or change the solvent. Once we have the pKa of our compound, then we can determine the log P and the solubility. So let's start with the log P. For log P determination, Sirius T3 offers the potentiometric technique. As the potentiometric pKa, the amount of sample needed is between 0.5 and 1 milligram, and this is depending of the molecular weight of this compound. The compound has to be ionizable. It can determine log P's for UV active and non-UV active compounds. The assay duration is longer. This is because before the data is collected, the two layers of octanol and water needs to separate because the electrode only can read in the aqueous layer. Once the data is processed, then we have the lipophilicity profile, the log D versus pH, and this graph and table is calculated. The software includes a range of partition solvents like decanol, toluene, etc. So usually the log P determination is in octanol. So I will refer to it for the rest of this presentation. Experimental conditions. So the pKa of the sample also need to be determined. pKa and log P have to be measured at the same conditions. For instance, if the ionic strength is, for example, 0.1 molar sodium chloride, and the temperature is 37, this is for the determination of the log P, then means that the pKa that is used for the determination of the log P needs to be done at the same ionic strength and the same temperature. Then, as we commented already for potentiometric technique, some of the bullet points previously commented for will be applicable for pKa as well. So, for example, it's advisable that to weigh the sample in the vial as a solid. The amount of sample depends on the formula weight and molecular weight, and for that, the buffer index profile needs to be checked and to ensure that the experiment will be run with enough sample, and it needs to be around 1 millimolar, the initial concentration. The model design needs to include the formula weight and molecular weight with all counterions present, the aprotic and protic. Start the experiment where the sample is ionized. That will be low pH for the bases and high pH for the acids to help dissolution. And there are three different models for log P determination, and they are depending of the amount of octanol and water that is used. Log P medium is for sample which log P values between 0 and 2.5, more or less. Higher than 2.5 is considered high, and lower of 0 is low. As is shown in the ionization graph here on the left, the three pKa titrations need to be equidistant, so same distance between them. These titrations are the pKa curves, meaning that is the pKa determined in the presence of octanol. Moreover, because the pKa can shift differently from one titration to another titration, then we need to check the index profile of the sample for the three titrations. And it needs to be between pH 3 and 11, more or less, as is shown in this graph. So then how to set up the right volumes of the experiment? The green curve here, this is the pKa determining water. So that means that this is water conditions. The blue curve, the pKa, these are the pKa's determined in octanol conditions. So if we are adding more and more octanol, the curves are going to shift more and more to the right. And adding more water, the curves will shift more and more close to the pKa in water, which is the aqueous conditions. How good is my data? As we are in potentiometric technique, this slide is similar to the potentiometric pKa. So again, check your buffer index of your sample and check especially in the third iteration as is when it's more dilute. Again, the experimental points needs to fit the theoretical curve, and moreover, the data experimental points has to behave in the same way as is the theoretical lines, and is shown in this graph here. No errors and warnings has to appear when it's processing the data. However, the amount of octanol to add has a limitation, and this is the Scherrer limit. So in this graph here, this is a determination of log P for imipramine. So you can see that adding 5 microliters of octanol, this is the black curve is the pKa determining water. So we have 5 microliters of octanol, we have this shift. Then we add 20 microliters of octanol, we have more shift and more for the red. However, at the end, you can see that here, these three curves are overlap. So the Scherrer limit is reached. So that means that no matter how much octanol we are going to add, because we are working like in pure octanol conditions, then for the people that normally use the log R graph, the best log P design is located here in the corner of this curve. So one titration on the Scherrer limit, one titration more or less in the corner, and another in the slope. Again, check precipitation. However, as you know, we are not using the UV probe. So the way to check precipitation is to look the unusual point behavior, like this one here. So you can see that the data points are closer one of each other. So this effect could be precipitation. Another way to observe if the sample precipitate or maybe it's not completely dissolved is checking the behavior of the pKa curve. If the data points are in a different trend in comparison of the theoretical lines, this effect will manifest that the sample maybe wasn't completely dissolved. So in this graph here, you can see that the experimental points are following the trend green, red, and blue. However, the expected trend should be blue, red, and green. Sorry. So the data points are not going to fit the lines when the data will be refined. So this could be a reason of that the sample was precipitated or not completely dissolved. So here we are going to talk about check salt solubility. So for that, we need the pKa of the compound, as we were talking for the log P determination. So for potentiometric technique, solubility assays are starting for around 3 millimolar, 3 milligrams for sample. However, this quantity of sample depends more or less of the solubility of the sample. So maybe we will need more solubility, more amount of sample to perform the solubility. The compound has to be ionizable, and yes, and we can determine solubility for UV active or no UV active compounds. The duration of the assay could be around 40 minutes, more or less. It's depending of the relief of the nature of the sample. And once the data is processed, log S versus pH graph and a table is also calculated, as is shown in this graph on the right. So a range of conditions are available, like aqueous or co-solvents to use, or the presence of excipients and additives. So the pKa's of the samples needs to be determined, and they have to be determined in the same conditions as the solubility is determined. For example, if we change the ionic strength for our solubility, then we have to use the same ionic strength for our pKa, the same for the temperature or the solvent use. And not only the solvent, the percentage of the solvent that we are using. So as we are in potentiometric technique, so more or less the same bullet points are going to be used here, like the sample is weighed in the vial as a solid. The model design needs to include the formula weight, molecular weight with all the counterions present, aprotics or protics, and start when the sample is ionized, low pH for the bases and high pH for the acids. Additionally, check that your sample does not absorb around 500 nanometers, and this is the wavelength set up as default to detect precipitation. So the graph shown in this slide, you can see that they have a strong absorption around 500. When we were running this assay, precipitation happened during the analysis, yes, however, it wasn't detected. But if, for example, if the wavelength that had been set up at 600 nanometers here instead of the 500, the precipitation will be detected. Checksol has two types of assays. The Checksol for samples that can supersaturate, or chasers, and curve-fitted for samples which cannot supersaturate, or non-chasers. How good is my data? So to have a successful solubility result, the sample needs to be completely dissolved and precipitate during the same assay. If the sample supersaturate, then it's a chaser. And the chasing always needs to happen around the middle of the curve, not at the beginning and not at the end of the assay. If Checksol assay is performed and the sample does not supersaturate, then repeat the assay using the curve fitting method. If the sample is too insoluble in water and the need of co-solvent is needed, so at least 3 titrations at different percentage needs to be carried out. And the extrapolation to aqueous conditions will be performed with using the linear extrapolation. Summarizing. So blanks needs to be performed in the same conditions as any of the physicochemical properties determined, so pKa, log P, or solubility, same ionic strength, and same temperature, except when we are using co-solvents, because the software will correct automatically the 4+ parameters. pKa's needs to be performed under the same conditions as the log P and the solubility assay. For example, if a log P is determined using the ionized water and is at 37 degrees, pKa needs to be determined in the ionized water and at 37 degrees. And not only that, the blank for the pKa and the blank for the log P needs to be performed as well in the ionized water and at 37 degrees. To finish this presentation, I would like to comment the application note Pion Sirius T3 user maintenance guide. So this application note can be found in our website. in resources library. And it's a good guide that which explain which task has to be done every day, every month, every 3 months, and every 6 months. So for example, for the tasks that they need to be done daily. So yes, rephrase the storage solution as we saw, like the pH7 buffers, the solvent and surfactant wash, flush the reagents, but this will be automatically. Calibrate the spectrometer, run two cleanups, one at each direction, and finally a blank. So for the weekly tasks, refill the electrode, and then you need to check the volumes of the flowing wash and waste volumes. And that means that you need to check that the volumes in the containers has to be the same as the volumes that the software is tracking. And not only for the flowing wash and waste containers, you need to do it as well with the reagents volumes. That means all the bottles, reagents, and solvents that you have in the tray. Yes, the argon bubbler needs to be refilled because with time the water evaporates, and the ultrasonic bath needs to be refilled as well. So for the monthly task needs to check syringes and tube fittings, and this means that with time the syringes and the fittings are starting to be loose. Then is because it's monthly task, then some reagents will need to be replaced. And yes, the KOH concentration factor needs to be standardized with the KHP. For semi-annual task, we have that to clean the flowing wash and waste, and especially the flowing wash as bacterial growth can appear over time. Needs to check the autoloader alignment positions, and if you notice that the autoloader is starting to lose the alignment position, please contact Pion. Calibrate the turbidity sensor. If you are usually using the turbidity sensor and it needs to be calibrated, please contact Pion as well. So basically, any issue related with a bad functionality of the instrument or with unexpected results, or even if you need help to understand your result or if the data processing is challenging, please contact our tech support department for help. So we are now in the last slide. So any experimental assay cannot start until the warnings and the maintenance tab are resolved. Blank must be performed every day and they have to pass. KOH standardization must be performed every month and replaced every 3 months. pKa's log P's and pKa's solubility must be determined in the same conditions as their blanks. Good data will be shown as a good fit between the experimental data and the theoretical curves calculated by the software. All techniques included in T3 complement each other. So please use different techniques to confirm number of pKa's and results. If one assay does not give the expected results, please repeat the experiment, changing some of the conditions. So don't repeat the same experiment with exactly the same conditions. Take care of the instrument, follow the Pion Sirius T3 user maintenance guide, and if you need any help, please contact Pion. So thank you so much for attending this webinar. If you have any questions, please use the Q&A chat box and I will answer as much as I can in the time that we have left. Thank you.
All right, great. Thank you, Rebecca. And we did have a few questions come in. One of them came in fairly early on, and you touched upon it on your summary slide with co-solvents. If you're using something not on the list, contact Pion. The question is, what happens if I use a co-solvent that is not on the list? So I guess that question becomes, okay, if it's not on the list and they contact Pion, what happens next?
Yes, okay. If you are using a co-solvent that is not in the list, Yes, absolutely, contact Pion. But more or less what you need to do is, as it's not in the list, the software is not going to calculate the 4+ parameters using the data from the blank. So that means that before doing or after doing your essay, you need to run several blanks using the same percentages that you are going to use with your solvent for maybe your pKa. So in other words, if you run a pKa, for example, in ethanol, is in the list, but imagine that it's not in the list. And that is not in the list, and you run your pKa using 40, 30, 20 percentage, you need to run the blank at 40, 30, 20% in ethanol.
Okay.
I think this will answer the question.
Okay. A related question that came in is, when is MDM used as a co-solvent?
Yes, the MDM could be used as a co-solvent. And there are a lot of people that use as a co-solvent because it's solubilize a lot of the compounds. However, in the system, you will see that it's set up as when you prepare this co-solvent is in volumes 50% with the water. So that means that the percentage that you can use is not that high. I think that the maximum that you can use is 46% in the MSO. The reason is that Yasuda-Shedlowski is not linear, higher than this percentage. So this is the reason that is not available. And if you're using the MSO, please use the linear extrapolation, not Yasuda-Shedlowski, because the MSO is the dielectric constant of the MSO is not changing so much with the percentages, and this is crucial for Yasuda-Shedlowski.
Okay, very good. What were the electrode values that needed daily logging?
The electrodes values. You mean the millivolts?
I assume so.
Okay, the millivolts for the electrode needs to be between 30 and -30. And if you observe that your blank doesn't pass, then please check the millivolt readings. If the millivolts readings are out of these ranges, that could be that, yes, the electrode is deteriorating and is not reading properly. The reason for that could be accumulation of salts, or maybe the electrode is damaged. So in any of these cases, please replace the electrode.
Okay, thank you for that. Another question, if our sample absorbs at 500 nanometers, can we detect at another wavelength for solubility determination?
Sorry, repeat again, if the sample?
If our sample absorbance at 500 nanometers, can we detect at another wavelength for solubility determination?
Yes, absolutely. Because you are going to run your pKa before solubility, you will see the absorbance of your sample. Doesn't matter if it's UV or pH metric. You will see the absorbance wavelength graph, and is when you have to check where your absorbance, where your sample is absorbing. So if it's absorbing at 500, then yes, when you are doing your solubility, please set up the default absorbance, move it to 600. You can change the absorbance in the wavelength in the advanced settings when you are setting up your sample. If you cannot find it, please contact us and we will direct you directly to the right setup.
Okay, thank you. I think we have time for one or two more questions before we need to wrap things up. Here we have one. What do I need to do if the signal saturates the detector? Can I use the data?
Okay, okay, this has different yes and no. You can use the data if there is a part of your signal that is not saturated. So, okay, let me show that, because in the graph that I show this, where is that? This has to be here. Yeah, okay. For example, in this case, yes, we have that here the signal is saturated. However, here is not saturated because it's lower than 1.5. So in this case, you could use this range of wavelengths. However, if all your signal is saturated, then no, you cannot use the data, and you need to repeat the sample and wait less sample.
Okay, thank you. I think we have time for one more here. In the log P determination, I have precipitation. What can I do?
This is an interesting question. As I said, we have the problem that we don't have the UV when we are running log P, so it's quite difficult to see if the sample is failing because it's precipitating. As I said, one way is to see if the data points are close each other, or if the train of the 3 titrations is following the theoretical. However, if you realize that, yes, my sample is precipitating, you need to investigate when it's precipitating. It's precipitating because it's not enough octanol. That means will precipitate or not dissolve at the first titration, or is precipitating because I have so much water, or is because I have so much octanol. That means that precipitate, for example, in the last titration. So change the volumes, water and octanol, and try to find the best volumes that the sample is not precipitating. I know that is a little of try and error, but it's the only way to do it, really.
Okay, thank you for that. And we have a few more questions that we will follow up with after the fact, after the webinar, and we'll get those answers out to you. A common question that came up behind the scenes was, will this presentation be available after this webinar? The answer is yes, it's being recorded. And as soon as it gets processed and is ready, it will be sent out to you. Thank you, everyone, for attending. Thank you, Rebecca. I hope you enjoyed this webinar, and please join us for future webinars. And if you have any questions, contact us at pion-inc.com. And Rebecca, I'll just leave it to you for some closing remarks.
Okay, so yeah, thank you everyone to join today. And yes, please send over to us the questions and contact us if you have any problem with the instrument, that we will try to help us as much as we can. Thank you.